Welcome to Talk Tensors.
It is really great to be here.
So today we are looking at a technology that really feels like it is finally closing the loop on a problem that has been bugging the machine learning community for years. We are doing a deep dive into something that fundamentally changes how neural networks access information. It is the bridge between the old way, which was basically memorizing the entire internet, and the new way, which is actually looking things up.
Yeah, I mean, it is the shift from a closed book exam to an open book exam. That is the best way to think about it.
Exactly. We are doing a deep dive into Retrieval-Augmented Generation, or RAG, and I want to set the stage here because for anyone following the LLM space, large language models, we have sort of been in this bigger is better arms race for a while now. You look at the GPT family, you look at T5, and the logic has always been just make it bigger.
Right. That has been the prevailing orthodoxy in the field. If you want the model to know more facts, you simply have to add more parameters. You have to make the artificial brain bigger so it can store more information.
Right, and that leads to what the researchers here call the parametric problem. I want to start there before we get into their RAG solution. Help us visualize this problem. When we say a model like GPT or T5 has parametric memory, what are we actually describing under the hood?
So imagine you are studying for the most important exam of your life, and it covers everything: history, science, pop culture, geography, you name it. But there is a massive catch. You're allowed to read the entire internet, Wikipedia, every book, every news article during your study phase. But when you walk into the exam room, you cannot bring anything with you. No notes, no books, no phone.
It is the ultimate closed book exam.
Exactly. Everything you know, every single fact, every date, every chemical formula has to be stored inside your actual brain tissue. In neural network terms, that knowledge is stored in the weights or the parameters of the model.
Which explains why these models are so huge, right? If you want to memorize the population of every city in the world, you just need a lot of neurons. You need a massive amount of storage space within those floating point numbers.
And even then, even with billions of parameters, it is a lossy compression. That is the key insight you have to grasp. When you train a model like T5, you aren't storing the actual text of Wikipedia in a database. You are compressing the statistical relationships of that text into weights. It is like trying to memorize a photograph by describing it in code. You lose fidelity.
And because you lose fidelity, you get the three big failures we see in current state-of-the-art models. The first one is my favorite in a sort of dark comedy way, and that is hallucination.
The confident lie. Because the model is just predicting the next likely word based on statistical patterns, if it forgets a specific fact, say, who won the World Cup in 1986, it doesn't just say, I don't know, it looks at the pattern. It sees World Cup in 1986, and it knows a country name should mathematically follow. So it might just say Brazil.
Because statistically, Brazil and World Cup appear together a lot in its training data. The model is betting on probability rather than retrieving a hard fact.
Precisely. It fills in the blank with something plausible, but entirely wrong. It prioritizes fluency over factuality. It wants the sentence to sound good, even if the content is completely fabricated.
Then you have the second major issue, which is stagnation. This is the knowledge cutoff problem that drives everyone using these tools crazy.
Right. If your knowledge is baked into your brain cells, into the neural weights, you cannot just learn a new fact instantly. If the President of the United States changes today, or if a stock price crashes, a standard LLM does not know that. Its brain is literally frozen in the exact moment it finished training.
And to teach it that new fact,
you have to perform surgery. You have to retrain the entire massive network.
Which costs millions of dollars in compute and takes weeks or months. You can't just slip it a sticky note with the new info.
Exactly. So you have these super intelligent systems that are perpetually stuck in the past. And then the third problem is opaqueness. The model is a black box. If it says the answer is 42, you have absolutely no idea why. Did it read that in a book? Did it make it up? Did it conflate two different numbers? There is no provenance. There is no citation you can check.
So enter RAG, Retrieval-Augmented Generation. This deep dive is all about how this architecture says, stop trying to make the student memorize the whole internet. Just let the student bring the internet into the exam room.
That is the core paradigm shift. It decouples the reasoning engine, the part of the brain that understands grammar and logic and syntax, from the knowledge base.
It essentially gives the AI a library card.
A very, very fast library card.
Let us get under the hood, because this isn't just a simple Google search bolted onto a chatbot. It is mathematically much more integrated than that. The architecture has two main characters. I like to call them the librarian and the writer.
In the actual architecture, they're formally defined as the retriever. which is a specific probability distribution, and the generator, which is another.
Let us start with the librarian, the retriever. Its job is to find the relevant information, but it is not using keywords, right? It is not looking for the exact word cat and matching it to a document that contains the word cat.
No, that would be a sparse retrieval method like BM25, which is what old school search engines used for decades.
Yeah.
RAG uses dense retrieval. It is based on a system called DPR, or dense passage retriever.
Dense here refers to vectors. We need to explain this concept clearly because it is fundamental to how modern AI actually thinks about meaning.
Right. So in this system, every piece of text, whether it is a user asking a question or a paragraph sitting on Wikipedia, is converted into a vector. A vector is just a long string of numbers. You can think of it as coordinates in a highly complex, multidimensional space.
Imagine a map, but instead of just north, south, and east, west, you have 768 different dimensions. It is a hyper-complex coordinate system that humans cannot physically visualize.
Exactly. And the magic of embeddings is that the location on this high-dimensional map represents semantic meaning. The vector for the word dog will be mathematically positioned very close to the vector for the word puppy, even though they do not share any letters. They live in the same neighborhood of this high-dimensional city. Conversely, the vector for hot dog would be far away, perhaps over in the food district of the map.
So the retriever uses a bi-encoder architecture to navigate this. What does that mean structurally for the system?
It means you have two separate neural networks working in tandem, both based on a BERT-based architecture. One is the query encoder. You type in a prompt like "Who directed Inception?" It crunches that text and spits out a single vector representing the semantic meaning of that question.
And then you have the document index on the other side.
Yes, this is the library itself. The setup here is wild. They took all of Wikipedia, about 21 million distinct 100-word snippets, and ran every single one through a document encoder. So now, Wikipedia isn't text anymore in this system. It is a massive cloud of 21 million points floating in that 768-dimensional space.
So when I ask my question, the librarian isn't reading books. It is doing geometry.
It is performing maximum inner product search. It takes your question vector and looks for the document vectors that have the highest dot product, which essentially means they're pointing in the exact same direction. The mathematically closest vectors are the most semantically relevant documents.
And this happens incredibly fast. They use a library called FAISS for this. Why is that specific library necessary?
Because checking 21 million vectors one by one, doing the complex math on every single point, would be way too slow for a real-time chat interface. You'd be waiting minutes for an answer. FAISS is an index heavily optimized for similarity search. It allows for sublinear search time.
Sublinear meaning it does not have to check every single document on the shelf.
Right. It basically clusters the vectors into regions. If your question vector lands in cluster A, the system completely ignores the other 99% of the library and just searches within that specific cluster. It happens in milliseconds.
Okay, so step one is complete. I ask, when did the Eiffel Tower open? The retriever zips through the vector space and pulls out the top K documents. Let us say it grabs the top 5 or 10 most relevant Wikipedia snippets. Now we hand those off to the writer, the generator.
This is component number 2. The generator in this specific architecture is based on BART large. BART is a sequence-to-sequence transformer. It is specifically designed to take text in and put text out. It is a very strong writer.
But here is the twist. It does not just take my question as the input.
No. This is where the augmented part of Retrieval-Augmented Generation comes into play. The model takes your input question, and it concatenates or physically attaches the raw text of the retrieved documents to it.
So the prompt that goes into the AI brain effectively looks like this. Here is some context from Wikipedia about the Eiffel Tower. Now answer the user's question, when did it open?
Essentially, yes.
Yeah.
But it is doing this for multiple retrieved documents simultaneously. And this brings us to the mathematical secret sauce of the whole framework, which is marginalization.
Marginalization. That is a scary word for a lot of people, even some developers. Let us break it down clearly. Why do we need to marginalize?
In plain English, the model treats the retrieved document as a latent variable. That means the model acknowledges a level of uncertainty. It essentially says, I do not know which of these 5 retrieved documents is the absolute perfect one to use. Maybe document 1 is highly relevant but misses the specific date you asked for. Maybe document 2 is completely perfect. Maybe document 3 is about a small replica of the Eiffel Tower in Las Vegas and is totally misleading.
So it hedges its bets across all of them.
It calculates the probability of generating the correct answer given document 1. Then it calculates the probability given document 2, and so on for all top K documents. And then this is the marginalization part. It sums those probabilities together.
It is like consulting a panel of experts. Expert A says the answer is 1889 with 80% confidence based on their book. Expert B says 1889 with 90% confidence based on theirs. Expert C is reading a totally irrelevant document about hot dogs, so their confidence in generating a date is near zero. The model aggregates all that mathematical confidence to say the overarching consensus is 1889.
That is a brilliant analogy. It allows the model to be incredibly robust against bad retrieval. If the librarian accidentally grabs one terrible document, the writer can effectively filter it out because the probability of generating a coherent, accurate answer from that bad document is mathematically tiny. The math naturally suppresses the noise and amplifies the signal.
Now we have to make a major distinction here. The framework presents two very different ways to do this integration. This is the RAG sequence versus ARG token debate. And this, to me, is where the architecture gets really clever and powerful.
It is the most critical design choice in the system. Let us start with RAG sequence.
Well, walk us through it.
In RAG sequence, the model retrieves a set of documents, but for each specific answer it might generate, it uses only one document to generate the entire output sentence.
So if it decides to heavily weight the Eiffel Tower history article, it is completely locked into using that specific article for the entire duration of the answer.
Correct. It calculates the probability of generating the whole sentence. The tower opened in 1889, based entirely on document A. Then it does the same calculation for the whole sentence based on document B. Then it sums those final sentence level scores.
This seems really intuitive for standard factual questions. If I ask who is the president, you want one solid source of truth to build the sentence around.
Exactly. RAG sequence is generally better for straightforward open domain question answering, where the answer is a concrete fact cleanly contained in a single passage. You do not want the model jumping around confusedly between sources.
And then we have RAG token, and this is where things get genuinely trippy.
RAG token allows the model to switch which document it is relying on per word.
Literally per word, or strictly speaking, per token.
Per token, yes. So for the very first word of the answer, it might mathematically rely heavily on document A. For the second word, the attention might shift entirely, and it pulls from document B.
That sounds like absolute chaos. Wouldn't that just create a Frankenstein sentence that makes no grammatical sense?
You would think so, but because of the transformer's underlying attention mechanism, it actually allows for incredible synthesis. Imagine you ask a complex, multi-hop question like, who directed the movie that starred the lead actor of Titanic?
Okay, that is a great example. To answer that, I, as a human, need two separate facts. Fact 1, the lead actor of Titanic is Leonardo DiCaprio. Fact 2, I need a list of directors who have worked with DiCaprio.
Right. A single document in Wikipedia might not have both of those facts cleanly laid out. One Wikipedia page is purely about the movie Titanic. Another page is purely about the movie Inception.
So ARG token can look at the Titanic document to figure out the DiCaprio part, and then literally mid-sentence pivot its attention to the Inception document to find Christopher Nolan.
Exactly that. It aggregates the probabilities at each individual token step. So when it is trying to generate the actual name Nolan, the probability signal from the Inception document spikes dramatically, overpowering the Titanic document for that specific word.
It is synthesizing a completely new thought from disparate sources. That is so much closer to how a human researcher actually works. We do not just read one book and copy a sentence. We cross-reference. We pull a noun from over here and a verb from over there to write an original essay.
And the benchmark results completely bear this out. RAG token absolutely shines in generative tasks where the model needs to compose something highly original rather than just extract a static fact. It allows for a level of nuance and grammatical flexibility that RAG sequence just cannot match.
I want to pivot to how this whole thing actually learns, because we said earlier we aren't retraining the brain of the model in the traditional expensive way, but something has to be trained to make this work, right?
Yes, of course. This is an end-to-end training process. They initialize the retriever with pre-trained BERT weights and the generator with pre-trained BART weights, but then they train them jointly on a task.
So the librarian and the writer are basically going to school together.
They are learning to cooperate. The generator learns to write better answers based on the specific type of documents the retriever finds. But crucially, and this is the cool part, the retriever learns to find better documents based on what actually helps the generator produce the right answer.
That is the magic of backpropagation. The error signal flows all the way back from the final word generated through the writer and into the librarian. The generator effectively tells the librarian, hey, that document you gave me was garbage. Next time, look for something that explicitly mentions dates when the user asks a when question.
Exactly. The system self-optimizes its own retrieval strategy. The librarian gets better at finding useful documents, and the writer gets better at reading them. However, there is a massive engineering hurdle here that we have to discuss.
The major bottleneck.
The document encoder. Remember we said we turned 21 million Wikipedia chunks into high-dimensional vectors?
Yes, that massive frozen cloud of points.
Well, if we update the neural weights of the retriever during this joint training, specifically the document encoder part, the mathematical definition of all those vectors changes. The vector for Eiffel Tower suddenly shifts slightly to the left. The vector for haunt dog shifts up.
Which means we would have to reprocess all 21 million documents.
Every single training step. Because if the map changes even slightly, you have to resurvey the entire landscape to know where anything is.
That would be computationally impossible. You would just be burning millions of dollars of GPU cycles rereading Wikipedia constantly.
So the researchers used a brilliantly simple hack.
I love a good engineering hack.
They completely froze the document encoder. They never trained the part that creates the library index. They only fine-tuned the query encoder, which is the part that processes your input question.
Oh, wow. So the library shelves are literally bolted to the floor. The Dewey Decimal System does not change at all. The vectors for all the Wikipedia books are permanent.
The query encoder gets smarter at understanding your messy handwriting on the request slip. It learns to mathematically map your question into the specific vector space where the right answers already live.
Yeah.
It learns to meet the documents where they are rather than moving the documents.
That is incredibly efficient. It saves massive amounts of compute and makes this architecture actually viable to train.
And it enables the single most impressive proof of concept in the entire deep dive, the knowledge swap.
Yes. This was the exact moment I realized this is not just an incremental algorithmic improvement. This is a totally new paradigm for AI.
The world leaders experiment.
Walk us through this in detail. This is the aha moment for anyone listening who builds enterprise AI.
So they took a fully trained RRAD model. It was trained using a Wikipedia dump from December 2016.
Okay, so as far as this neural network knows, Obama is president of the US, the UK is just starting to think about Brexit, and the year 2020 hasn't happened yet.
Right. They sit down and ask it, who is the president of Peru? The model searches its index and answers with the 2016 president, Pedro Pablo Kuczynski.
Standard behavior. It is retrieving accurately from its 2016 library.
Then, without retraining the neural network at all, without touching a single weight in the generator or the query encoder, they just swapped the hard drive. They unmounted the 2016 FAISS index and mounted a brand new 2018 index.
Just swap the reference library, literally like taking out one USB stick and plugging in another.
And instantly, at test time, they asked the exact same question. Who is the president of Peru? And the model smoothly answers Martin Vizcarra, who is the 2018 president.
That is the hot swap capability. And think about what that means for practitioners listening right now. If you are a massive company and you have a complex employee policy manual, you do not need to spend $100,000 training a new LLM every time HR changes the vacation policy.
You just update the PDF in the folder, reindex that one document into the vector database, and you are done. The model's brain stays exactly the same, but its knowledge updates instantly.
It definitively proves that the model has successfully decoupled reasoning from knowledge storage. The reasoning how to frame a grammatically correct sentence about a president is locked in the neural weights. The knowledge, the actual name of the guy, is in the vectors.
It is modular AI. Software engineering has always been modular. You always separate your database from your application logic. But deep learning has been this massive monolithic blob until now. RA brings that essential software engineering modularity to neural networks.
Let us look at the scoreboard. Because having a cool modular architecture is one thing, but if it gets the answers wrong, nobody in the industry cares. They ran this against the big dogs, specifically the closed-book T5 model.
And remember, T511B is an absolute monster of a model, 11 billion parameters. It requires massive infrastructure just to run inference. RA large, the model tested here, is only about 626 million parameters.
So RAG is roughly 5% the size of T5. It is a total David versus Goliath scenario.
David won. They tested on open domain question answering. These are rigorous data sets like natural questions, which are real Google search queries, trivia QA, and web questions. RAG set new state-of-the-art results on all of them.
On natural questions specifically, it hit 44.5% exact match accuracy. That beat the massive closed book T5, and crucially, it beat specialized retrieval systems like Realm.
There was a specific stat in the paper that really stood out to me about the no answer scenario.
Explain that for us.
So previous retrieval systems were mostly extractive. That means they find a document, read it, and simply highlight the text that answers the question, like using a physical highlighter pen on a page.
Okay, like doing CTRLF on steroids.
But what if the document says, the sky shares its color with the ocean? And the user's question is the sky blue? An extractive model completely fails there because the specific word blue is not in the text to be highlighted.
But our RAG is generative.
All right, it reads the sentence, the sky shares its color with the ocean. It uses its parametric brain to know that the ocean usually implies the color blue, and it physically writes the word blue. It can synthesize the correct answer, even if the string of characters is not verbatim in the retrieved text.
It is combining reading comprehension with semantic synthesis. That is a massive leap over simple search and highlight extractors.
Now, where RAG really flexed its muscles, and this is probably my favorite part of the experimental design, was the generative tasks. They ran a Jeopardy experiment.
I love this. Jeopardy is notoriously incredibly hard for AI to play.
It is. The format is totally inverted. You get the answer and you have to generate the question. So the prompt is, in 1986, Mexico hosted this event. And the output has to be, what is the World Cup?
It requires highly specific factual retrieval, but also really weird, rigid syntax. It has to be phrased as a question perfectly.
Standard generative models like BART or GPT-2 are usually terrible at this task. They hallucinate wildly or they get stuck in repetitive generative loops. But RAG token absolutely crushed it here. It beat the baseline BART model significantly.
And this is where the human evaluation came in, right? They didn't just trust the automated BLEU scores.
No, they had actual human raters evaluate the responses blindly. The humans consistently found RAG token to be far more factual and far more specific. A standard BART model would often generate generic, safe questions like, what is a history book? Purely because that is a high probability, syntactically safe sentence.
It is hedging. The model does not know the specific fact, so it says something incredibly vague that technically cannot be proven wrong.
Exactly. But RAG would boldly generate who is the author of A Farewell to Arms because it actually found that specific entity in the index. It was not afraid to be highly specific because it had the source material right there in its working memory.
And it was evaluated as being much more diverse in its language. It didn't get stuck in those annoying text loops.
Which is a very common failure mode of pure parametric models. They get stuck in a probability rut and repeat the same phrase. RA gets unstuck because the retrieved documents constantly inject fresh vocabulary and context into the prompt for it to pull from.
The third major benchmark they ran was fact verification, the FAISS dataset.
This is a strict classification task. You give the model a claim, like the Roman Empire fell in 1492. The model has to classify it as supported, refuted, or not enough info.
And usually, to do this well, engineers build massive, complex pipeline systems. A separate system to find documents, another system to read them, a third system to check logical entailment.
Right. But RA tackled this end-to-end. Without any special gold standard supervision telling it which specific evidence sentences to look at. It just figured it out natively, and it got within 4.3% of those highly engineered, complex pipeline models.
That is incredibly impressive for a general-purpose architecture. It is not designed to be a specialized fact-checker, but out of the box, it is almost as good as one.
It just shows the raw robustness of the approach. If you can reliably retrieve the truth, verification inherently becomes a much easier mathematical problem.
Let us pivot to the analysis section of the deep dive, because asking why does this work is just as important for the listener as does it work.
The most exciting part of the analysis for me is the interpretability. We mentioned earlier that LLMs are frustrating black boxes. Our RAG is, let's call it a glass box.
Because we can literally see what it's reading in real time?
Exactly. When our RAG generates an answer, we can look at the top K retrieved documents it loaded. We can say, oh, it thinks the answer is X because it's read this specific Wikipedia article, and we can go read that article ourselves.
There is a fantastic visualization in the paper regarding Ernest Hemingway.
Yes, figure 2 in the paper. They visualized the internal attention or the posterior probabilities of the documents, while the model was token by token generating a Jeopardy question about Hemingway.
So the model is writing the sentence. It starts generating the words, "The sun also rises."
And you can see mathematically on the chart that the model is heavily focusing on document 1, which is the Wikipedia entry for the novel The Sun Also Rises.
Then the sentence continues.
Is a novel by this author of A Farewell to Arms.
And at that exact moment, right when it needs to bridge those two distinct concepts, the focus visually shifts. The probability weight for document 1 plummets, and document 2, which is the entry for A Farewell to Arms, spikes massively.
It is literally switching which book it is looking at mid-sentence.
It validates the argue token mechanism perfectly, but it also reveals something much deeper about how AI is learning to write. Notice that it did not need to retrieve a document to generate the bridging words, "Is a novel by this author."
Right. That is just grammar. That is syntax.
That is the parametric memory at work. The baseline BART model knows how to write fluent English sentences. It knows the rigid structure of a Jeopardy question. It uses its internal brain for the grammatical scaffold, and it reaches out to the external library purely for the bricks, the specific entities, the book titles, the dates. Parametric versus non-parametric synergy. The brain provides the scaffold, the library fills in the bricks.
And if the retriever fails, say the library is closed or the search returns garbage, the parametric memory can sometimes save the day. It might actually know a little bit about Hemingway in its own weights, but the combination of both systems running simultaneously is far superior.
Now, we have to be honest here. It is not all sunshine and perfect accuracy. What are the real limitations of this architecture?
The biggest one is somewhat obvious: Wikipedia dependence.
You are only exactly as smart as your library.
Exactly. If the answer simply is not in the vector index anywhere, RG is going to struggle. It is certainly better than a pure hallucination machine, but it cannot invent factual knowledge that does not exist in its source material.
And if the source material is fundamentally wrong,
then RJAG will confidently repeat the error. If Wikipedia has a malicious typo saying the moon is made of cheese, RJ will read that and tell you the moon is made of cheese. It is not a truth engine, it is a retrieval engine.
There is also a technical issue mentioned called retrieval collapse.
Yes, this is a training stability issue that researchers run into. Sometimes, during that joint training phase, the model gets mathematically lazy. The retriever stops actively looking for highly useful information and just starts returning generic documents, maybe the main page of Wikipedia or something completely irrelevant but safe.
And if the documents are garbage, the generator just learns to ignore them entirely.
And the model completely reverts to standard BART behavior. It essentially becomes a closed book model again, relying only on its weights. They have to use specific training tricks and hyperparameter tuning to keep the retriever engaged and mathematically hungry for highly relevant data.
But for practitioners listening to this, developers working in the field building applications today, why does this specific architecture matter right now?
2 words: scale and updates.
Let us break those down. Scale.
You can get generative performance rivaling an 11 billion parameter model with a model that is less than 1 billion parameters. That means you can run this on vastly cheaper hardware. You do not need a multi-million-dollar TPU pod to run inference for your users.
And updates.
We touched on this with the hot swap example. The real world is dynamic. RAG allows your AI to actually live in a dynamic world. You do not need to retrain, you just update the vector index. For enterprise applications, legal tech, medical assistance, live news bots, this is a non-negotiable feature.
It effectively kills the dreaded knowledge cutoff disclaimer we see on every chatbot.
It absolutely should, yes. It makes that a thing of the past.
Okay, this is the point in the deep dive where we take the safety rails off. We have looked deeply at the architecture, the complex math, the benchmarks. Now I want to go into the novel notions segment.
The speculation zone. I love this part.
Disclaimer for everyone listening, this segment is for entertainment purposes only. These are highly speculative ideas based on the trajectory of the architecture we just discussed, not actual commercial products that are necessarily built yet.
Though, looking at the tech, they probably should be built soon.
Novel notion number 1. I am calling this the schizophrenic encyclopedia, or maybe slightly more politely, the personality fact decoupling.
Okay, go on. How does this work?
We proved with the World Leaders experiment that you can instantly hot swap the index and completely change the truth that the model perceives.
Yes, the Peru president example.
So why stop at just updating boring facts? What if we created a single universal speaker model, a really good, highly eloquent generator brain, and we swapped the index to fundamentally change its cultural, political, or corporate allegiance instantly?
I see exactly where you're going with this. You load a flat Earth vector index.
And suddenly the model becomes an ardent conspiracy theorist. But, and this is the key, it speaks with the eloquence and grammatical perfection of a university professor. It uses the deep reasoning capabilities of BART, but relies entirely on the facts of a fringe conspiracy forum.
And then you could instantly hot swap a corporate legal index.
And it immediately becomes a hyper-compliant, risk-averse HR bot. Same exact brain, completely different soul.
It creates a fascinating and somewhat terrifying future for brand AI. You do not spend millions training a custom Disney bot or a custom Fox News bot. You train one master foundational model, and you just feed it a different vector library to completely shape its worldview. It implies that bias in AI isn't just permanently baked into the weights anymore. It is modular. You could literally sell bias packs as downloadable content.
Exactly. Download the 1950s worldview pack for your AI for only $9.99.
It certainly makes the alignment problem much more dynamic and arguably much harder to regulate.
Novel notion number 2. I'm calling this the episodic memory personal assistant.
Taking RAG to a hyper-personal level.
Exactly. Right now, the index is Wikipedia, public general knowledge. But what if the vector index was a real-time encrypted stream of my entire life? Every email I send, the transcripts of my meetings, my credit card receipts, my real-time GPS location history.
This would directly leverage that RAG token synthesis mechanism we discussed earlier.
Yes. Imagine I asked my phone, why was I so stressed out last Tuesday afternoon?
A standard parametric model cannot possibly answer that. It has no data.
But a Argusho token model retrieving from my personal life index. It pulls document A, which is my calendar showing a meeting with my boss. It pulls document B, which is my Apple Watch health data showing my heart rate was elevated. It pulls document C, which is my Gmail, showing an urgent project deadline subject line.
And it synthesizes them token by token. It replies, you were stressed because you had a meeting with your boss, where your heart rate spiked to 110 BPM, likely due to the urgent project deadline discussed in your email that morning.
It constructs a completely original narrative explanation of my life from disparate, unconnected data points. It is not just search. It is true synthesis of the self.
That is the holy grail of personal AI assistance.
Yeah.
But the privacy implications of vectorizing your entire waking life and feeding it into a generation engine are... well, they are massive.
Oh, massive. The security risks are astronomical, but the daily utility, unbeatable.
It really brings us back to the core underlying strength of Retrieval-Augmented Generation. It is fundamentally about connecting dots that were never explicitly connected in the training data.
So let us wrap this deep dive up. What is the one big takeaway for you, for our listeners, regarding ARGAG?
For me, ARG represents a philosophical shift from learning facts to learning how to find facts. It acknowledges that the world is simply too big and changes too fast to memorize.
We are moving toward a paradigm of models that are smaller, smarter, and can actually verify their sources rather than relying on massive black boxes that just hallucinate with absolute confidence.
It is a much-needed step towards humility in artificial intelligence. Ideally, anyway.
I really like that framing, humility through retrieval. I think that is a perfect place to end. That is it for this deep dive.
Keep building, everyone.
Talk Tensor signing off.